Hi everyone. I will be fast here. So today my topic will be machine learning application in airspace operation, from terminal airspace to dynamic configuration. First of all, a little bit background knowledge. Basically, air transportation faces challenges with increasing demands. You can see from the left figure is the total number of carrying passengers is increased exponentially. And even though we know that COVID is have severely battered the industry, actually the newest data show that the global RPK in November 2023 reaching 99% of pre-pandemic November 2019 levels, which means the challenges still exist. So how to solve the problem? To provide a better ATM system in the future, researchers and industry are turning to machine learning as a powerful tool for driving ATM technology evolution. So basically FAA, ICAO, and Air Control, they established groundbreaking projects and plans. So one of them is CESA, also my sponsor, so thank you, CESA. And these initiatives recognize the crucial role of machine learning in achieving their objectives. So the objective of this presentation is that first, introduce the current research of machine learning applications in terminal airspace and dynamic airspace configuration, and then provide 2 case studies for both research direction, and at last, discuss the potential future directions in this research area. So first of all, sorry. So first of all, it doesn't show here. So what is terminal airspace? So basically, terminal airspace is the bottleneck of air traffic control systems. It has natural high traffic density and capacity, manage both departure and arrivals. And for these 2 categories, arrivals are more complicated because if there is a delay for arrivals, you need to hold it in the air, which creates extra fuel burns and also decrease the safety score for such flights. And there are challenges. In one study from The Economist, they said that if you have a better arrival operations, you can save 5 to 10% of fuel per flight. But yet, despite the challenges, we still have potentials for this research in terminal airspace because you have a higher accessibility and quality of flight-related data in terminal airspace. And also, you can combine your study with some local detection instrument, which is, for example, wake vortex particle detection on the runway, something like that. So here I will briefly describe some of the ML applications in terminal airspace research. The first criteria will be predict and optimize the traffic characteristic in terminal airspace. The first one will be ETA predictions, which Daniel has some very good work in these directions, and also go around predictions. And the last one will be reinforcement learning for optimal flight path, which due to the environmental friendly and also fuel burn, something like that. So the other direction will be modeling the local weather impact on air traffic performance. So for this direction, we have flight trajectory prediction under weather uncertainty, and also data-driven weather impact quantification. So in my case study, I will briefly mention something I did about ETA prediction and data-driven weather impact quantification in the case study sections. So next, we'll be introducing the concept of dynamic airspace configurations. So for terminal airspace research, the scope of the research is mainly focused on the approach stage and coming stage of the airspace, which is basically like this. And for the dynamic airspace configuration, we are actually considering larger area and more flight levels, which introduces more data, more interesting research, but also increase the uncertainty and complexity. So the concept of dynamic airspace configuration is sort of a recent concept. So it's first proposed in 2007. It says that future airspace needs to be flexible, dynamic, and adaptable based on traffic demand, equipage, and weather. So for the current state of art, there are basically 2 different ways to approach this target. The first one is partition. So basically, you will have a whole piece of volume of airspace that you can divide it into sectors. A second way to do it is grouping. So basically, we already have some sort of basic volume, or we call it building blocks, that ATCO, air traffic controllers, are very familiar with. So we try to grouping this very small basic volume together to grouping them as the sectors so that to try to fix the traffic demand distribution. So intuitively, the second method is like more user-friendly because ATCO, they're already familiar with those kind of building blocks they use for years. So it avoids that you try to like partition a whole airspace every time when there is like you need to block some of the building blocks and then you create something new for the air traffic controller, which is actually not helping anything. So this is also what I will focus on. I will talk about the grouping of dynamic airspace configuration. And also because this is a new project I joined this project in January, so it will be mainly discuss the potential of machine learning in these directions. So this is also an illustration of the DAC. Basically, it shows that for different time periods and for different flight level, they can configure different types of sectors together and then create the working sector for the air traffic controllers. It's for the Madrid ACC. So briefly talk about the model characteristic of DAC. As before the whole session, I talked to Professor Delahaye about this, and he also mentioned about that the importance of operational constraints. So here I show something that we must concern about when we are doing dynamic airspace configuration. The first thing would be the workload balance, that you try to split the workload for each air traffic controllers like in a good way, so that like so the workload is well distributed. And for the shape constraints, we don't want the sectors for each traffic controllers not compact. They need to be all in together and connected with each other. And one of the very important constraints is the traffic flow convexity. So for each sectors, it doesn't need to be shape convex, but it needs to be convex to the direction of the traffic flow. This is very interesting because that means because the concept of traffic flow convexity is a smaller concept than shape convexity. So that means we are not necessarily creating something that is shape convex, but flow convex. The last important group of the constraint is the robustness. We want it to be robust to the traffic flow distribution, robust to sudden disappear of some blocks because of weather, because of restriction, because of use of higher airspace or urban airspace, something like that. And the last thing will be computational efficient. If your algorithm is very fast, it can handle the dynamic traffic distributions. So next, I will go into the case study, and I'll be very fast. So the first case study will be the Hong Kong International Airport case study. So why we choose it? Because it has a lot of traffic and the weather is very, very bad. So that's why we choose it. And in this case study, we involve like 433 flight information data, 433,000 flight information data, 58,000 ADS-B data, and then 58,000 local weather report and 4,000 something local radar image. So basically, I want to show that machine learning actually can help to enhance the consideration of adverse weather for the whole operations. So the first piece of work is the weather impact quantification models. So here I only shows the core of my model. So basically it's a Bayesian hierarchical model. So why we choose this model is because we can use the distributions to describe some of the local parameters of the mean trend functions. So for the mean trend function inside the blue box, basically we use this to describe the similar deterioration properties for free airport traffic matrix, including the mean delay per hour, cancellation rates, and delay rates. So we use this model. Actually, it is transferable to other airports. Basically, it depends on the data analysis. We have some dangerous phenomena that is very important for Hong Kong, including thunderstorm, shower, and cumulonimbus. So based on this model, we can actually quantify the impact of dangerous phenomena, which we cannot do with like the current methods. And because we're using the Bayesian approach, it actually ensures the models updatability and uncertainty, so which is very important because updatability, that means that you can consider like climate change in your model, and uncertainty, as I said, that like combative weather, you might know it like 10 minutes before it comes, so that's also very important. And next, obviously, we have this weather impact quantification model, so how do we use it? So one is that it's explainable, but the other one is that we tries to input it into like a machine learning model, into a supervised learning model. We try to predict the arrival transit time prediction using our model. So we make a comparison between the conventional map weather algorithm developed by Eurocontrol. So basically, it's an expert-based model, expert-based algorithm. So we use our machine learning Bayesian-based model to compare and see what's the difference of the predictive accuracy. So we test XGBoost, LightGBM, MLP, random forest, and KNN. It shows that XGBoost has the best like baseline, so that we just compare XGBoost result. Basically, for normal cases, error reduction is like twice more crucial than the commonly used AppMap weather algorithm. And for the extreme weather cases, actually we can reach a 4% predictive error reduction and also still perform better than the AppMap weather algorithms. So this is the overall predictive accuracy combined with other things we consider, like the trajectory, topology, something like that. And the best performance actually can reach like around 7% for both cases. And this kind of high like predictive accuracy for arrival transit time actually can potentially benefit the arrival sequencing optimizations. So the next case study will be about dynamic airspace configuration. So because this part is like very small, so I will try to be very fast. And so we consider like higher airspace because higher airspace is very important. More and more flights are flying in the higher airspace because they want to save fuel, right? So, okay, this is the MILP of the model. So I will skip this part, and I just want to emphasize that if you consider traffic characteristic in the model, what happens? So basically, these are two different images you consider without traffic characterization and with traffic characterization. So, so I want everyone to look at the middle of this image. So basically, we don't want this kind of phenomenon happens when a trajectory cross one of the sector in 2 short times. So when we consider traffic characterization, actually it can avoid because as you see for this sectorization, it doesn't exist. So for this criteria, actually one research direction called the traffic characterization using unsupervised learning can help to enhance this performance if we try to include this kind of information into the constraints, not only in the objective functions. So in conclusion, machine learning shows capabilities in solving practical problems of both cases, basically enhance the understanding of weather and also can predict the arrival transit time to demonstrate robustness under normal situation and extreme weather situation. The last one is that it's also, the unsupervised learning also shows potentials in DAC in this optimization problem by addressing the flow complexity. So future directions. First, integration of prediction and optimization. This is very important. So I list 2 of the direction I think is very quite heated. So the first one is smart predict and optimize, try to put some of the components of optimization into the loss functions. And learning to optimize is also very important. And then the future ML applications in this DAC study, we can use graph neural networks to predict knot weights or edges weights, representing the basic volume workload and the accumulated commonality between basically the transition of traffic flow between 2 sectors. And the last one will be reinforcement learning for agent-based sector configuration. So thank you for listening. So I'm finished.